Okay. Good morning, all. Let us start our first day, first lecture. So, let me introduce your syllabus for today and let us go a little bit into your subject also. So, this is the syllabus that we are going to discuss as a part of your subject for first unit. So, this unit contains actually the fundamental definitions, fundamental concepts that you are going to need in other units of this subject and also in other subjects also. Okay, so concentrate on the basic definitions, equations, units, and etc. Okay, so we are going to solve problems also on each and every topic. As I said earlier, this subject is a little bit problematic subject. It contains a little bit of calculations and all. So, but don't worry, the problems are going to be very interesting and simple also. Okay, so I'm also going to tell you the basic thing how to solve a problem when it is given. Okay, so when we go there, you will find out how easy it is to solve problems. So for now, let's go into the introduction to our subject. So these are the textbooks that we are going to need, and if you see here, this is the most preferred textbook, I have to say. Of course, among these three, of course there are very good books other than this, but the standard of writing those books is very high and it is not much recommended for the beginners. So if you are comfortable with these with these textbooks, then you can go and refer those textbooks like Strength of Materials by Timchenko, okay, and Hibbeler. So, but as far as now, for the basic theory and basic understanding and basic problem solving, I believe these are very much sufficient, okay, and very good, I must say. And this Ramamrutam is actually meant for solving problems. There are many problems that are solved from small to larger difficulty. And this Rajput and Bansal are also very good, and these are very good at explaining the theory part, explaining the concepts and all. Okay, and besides this, I will also be providing you the lecture notes that could help you, but just don't depend on any notes. Try to learn something from the textbooks. Okay, you should depend on the notes for guidance, but in order to learn the subject, you have to go through the complete textbook. Okay, so let us jump into the subject. So, coming to the mechanics. Okay, actually, mechanics deals with the forces acting on a body and the response of that body, which is actually taking the forces. Okay, so as a broad classification, it is divided into three types: fluid mechanics, mechanics of rigid bodies, and mechanics of deformable bodies. This part of this mechanics is already dealt in the 1-2 semester of your curriculum, right? So this is actually engineering mechanics, mechanics of rigid bodies. And this fluid mechanics and mechanics of deformable bodies are the two subjects or the two important subjects, core subjects that you are going to learn in this semester. And coming to the mechanics of fluid deals with behavior of fluid. Okay, and coming to this mechanics of rigid bodies and deformable bodies, it deals with the behavior of solids. Okay, in order to, if you wanted to differentiate between fluid mechanics and mechanics of rigid bodies and deformable bodies, this is how you have to do at the fundamental level. Okay, these deals with the solids, and fluid mechanics deals with the behavior of liquids or fluids. Okay, so as for now we are going to concentrate on the mechanics of deformable bodies, and we call this subject by another name, strength of materials. Okay, so what is the difference between mechanics of rigid bodies and mechanics of deformable bodies? In the part of this rigid bodies, we actually assume that in mechanics of rigid bodies, we actually assume that the bodies are rigid. They are not going to deform under force or load. Okay, in simple words, if you take an elastic rubber band and if you apply some force pulling it apart, what happens is immediately the size or the length of that band is going to increase. That change in the length in the rubber band is nothing but the deformation. Okay, but in engineering mechanics we are going to assume that whatever the body we are dealing is a rigid body that is not going to deform. Okay, but actually if you see practically, that assumption is not not satisfiable. Okay, so why did we assume such a thing in our engineering mechanics? In the engineering mechanics, rather than studying the response of a body, we are trying to find out how the bodies are actually behaving with each other when certain forces are applied and all by a solid body. What are the forces, what are the reactions, and all those things. Okay, as a body. But here in our mechanics of deformable bodies, rather than the forces that are causing or applied on that body, we are interested in finding out or studying the response of a body to given force. Okay, so just like a human beings, when someone tries to pinch on our skin, on our hand, we immediately feel pain. We respond to something that is being done, right? And similarly, every material, every body has a manner or has a way of responding to external forces or external stresses. Okay, so that is what we are going to see in this mechanics of deformable bodies. Okay, so let's jump into our subject. So this figure here represents the same thing which I have told you in the previous slide. Okay, so fluid mechanics is nothing but dealing with the behavior of fluids, and these deformable bodies and rigid bodies deals with the solid bodies. Okay, so let's come to the basic two definitions of this subject. So before going into the further topics, you need to understand what is the meaning of elasticity and plasticity. Okay, so elasticity and plasticity is a property that a material is going to have, such as steel. Steel has elasticity. Aluminium, it has elasticity. Okay, so materials has these properties. So you need to understand what is the real meaning of these properties. Okay, so of course we have various definitions explaining this. The simple explanation to this property is the property of a body by virtue of which it tends to regain its original shape or size on the removal of deformable force is called elasticity. That is the basic definition. Okay, so what does that mean actually? So take a bar, take a rod, steel rod. Okay, try to apply force on both its ends, a tensile force away from each other. away from each hand, try to pull it apart. So what happens? Of course, you need to apply large amount of force, but still, as you apply, it is going to increase its length, it is going to elongate, it is going to stretch, right? So what happens if you remove the force and throw that rod on the ground, on the floor? What happens? Will the shape of that rod comes back to it? For example, see a rubber band. What happens when you stretch? It stretches. When you stop applying force and release that rubber band, what happens is it falls on the ground. If you see, you will find out that it has come back to its original shape. So that is the property elasticity. So because of elasticity, a body comes back to its original position when the forces which are responsible for that deformation are removed, just like in rubber band. Okay. But there is quite an opposite response also, that is plasticity. So some bodies are plastic in nature. They don't try to come back to its original shape. They just wanted to remain in their deformable shapes. Best example can be plastic and what not. The regular example, chewing gum can be taken as an example. Chewing gum is so plastic in nature, it has plasticity. So what is plasticity? Chewing gum is very soft, right? So when you try to stretch it with both your hands, just like a rubber band, it is going to deform, right? Increase in its length. But what happens if you just stop applying the force? Will it come back like the original rubber band? Will the chewing gum come back to its original shape or size? No, it won't come. It remains same, right? So there are different materials. Some materials behave elastically and some materials behave plastic in nature. Okay. But remember, elasticity and plasticity are the properties that a material can have at the same time. If you take a rod, it can behave as elastic material, but if the forces which you are applying on that exceeds or more than allowed, it reaches that plastic stage. It does not come back to its original position. Even rubber band, I just told you before that elastic, when you apply force and release the force, it comes back to its original shape. But if you apply so much amount of force for a longer time on the rubber band, even that rubber band is not going to come back to its original shape. That is what happens. See, when you try to use rubber band for something, for tying something, after few days, after some time, it gets elongated and it comes very larger in size, right? Rubber bands. So a material can have elasticity and plasticity at the same time. Okay. A material behaves elastically up to certain level of force, and if a force applied beyond that allowed or permissible, then that material is going to behave as a plastic material. Remember, plastic material does not mean plastic, normal plastic, right? Plasticity, plastic. So we call a body as a plastic if it does not come back to its original shape when the forces acting on it are removed. Okay, that is what I mean. So let us go into this slide. Types of forces and loads. Don't get confused with the term forces and loads. We are going to use these terms very much in this unit and in the other subjects also. So forces are nothing but loads. Okay. In our civil engineering terminology, generally, the forces acting on any structure are known as loads. Okay, for example, if I exert 10 kilonewton on a bench, what do you call that 10 kilonewton? You call it as force, right? But if that 10 kilonewton is applied on a column or a beam on a slab, okay, or on a bridge, then that force is called as a load. In the civil engineering point of view, we call that force acting on a structure as load. Okay, don't get confused, they are not different things. Okay, in some situations we call it as force, and in some situations we call it as loads. So loads can be classified into two ways broadly: body forces and surface forces. Okay, of course, you know the famous example of Newton sitting in the garden under an apple tree and an apple fell down because of gravitational pull and all those things, right? So let us take that example here. There are two forces, body forces and surface forces. So what are body forces and surface forces? So practically, if you wanted to apply any force on any body, you need to come in contact with that body, isn't it? For example, if you want to uh, hit something with a hammer, what you need to do is you have to hold your hammer with your hands and you have to use your hammer and hit that subject body, right? If you just swing this hammer in the air, will there be any force being applied on that body? No. మీ చేతిలో సుత్తున్నప్పుడు సుత్తుతో ఒక గోడ మీద మీరు ఫోర్స్ ఎగ్జర్ట్ చేయాలంటే వాట్ యూ నీడ్ టు డూ ఈజ్ యూ నీడ్ టు మేక్ ది వాల్ and hammer to come in contact. You have to hit the hammer on the wall. They should come to contact, isn't it? So the forces that are exerted by coming into contact are nothing but surface forces. The second one, surface forces. See here. Okay, direct contact between bodies. So what do you mean by body forces? So body forces are the forces exerted by a body on an other body without direct being in contact with that body. Oh, this seems to be something different which we have known, right? అంటే ఇప్పుడు అలాంటి గాల్లో నేను సుత్తు ఊపుతూ ఉంటే లేకపోతే ఎవరిని నేను కొట్టాలనుకుంటే నేను గాల్లో చేయి ఊపితే ఆడికి దెబ్బ తగిలినట్టు అనమాట. ఈజ్ దాట్ పాసిబుల్? Yes, it is possible. Of course, not to us, to earth. Okay, to earth it is possible. So what is this body force? Body forces are the forces that are experienced by a body due to another body without direct physical contact. Okay, so the perfect example is electromagnetic field and gravitational force. So just take this first example, gravitational force. Gravitational force is nothing but F equals to m into G. M into G is nothing but gravitational force. We denote this as W and we generally call it as weight, which is equals to m into G. Okay, this is the most famous Newton's formula. Yeah, he gave this formula after sitting on a tree. Sorry, under a tree. Okay, forgive me. So this gravitational force is nothing but mass into acceleration due to gravity. So every body that is nearer to the earth is going to experience this gravitational force even when it is not in contact with each other. Just like, say, for example, there is a person who is going in a plane and he wanted to jump out with a parachute, and he immediately jumped out of the aeroplane. Okay, just forgot the parachute. What is happening here is he is coming down, he is falling down, right? So what is happening here? Nobody is pulling him down, right? But he is coming down. Why not he go up? Because this gravitational force is being exerted by the earth even though they are not in contact with each other. Right, isn't it? Right. The person who is falling down is in the air, he's not in direct contact with the ground, but still he is experiencing that gravitational pull. That is what happened to that apple, to the apple tree. Okay, that is why it fall down, it didn't go up, right? So this gravitational force which is exerted on a given body is nothing but weight of that body. Okay, gravitational force experienced by any body is equals to weight of that body. Okay, for example, I am sitting in a chair. Okay, I am experiencing a gravitational force being exerted on me by the earth around me, right? So now my weight will be equals to the gravitational force. For example, let me calculate. Suppose, see this equation F equals to mg. Let us take that the mass of my body is something like 60 kg, 60 kg, and acceleration due to gravity is nothing but 9.81 meter per second square. Of course, for this case, let it be 10 meter per second square. So 60 is the 60 kg is the mass, and this is 10. What is this? 60 into 10, 600 Newton is the weight. So this is the general mistake many people do. Of course, there is a correct explanation why they are doing that. For example, if I ask you the what is the weight, you say something like 50 kg. Actually, what you are saying is mass of your body. You are not saying your weight, isn't it? If your weight, if your mass is 10 kg, 50 kg, if you take g as 10, your weight is 500 Newton. But why we say that weight is equals to 60 kg in the normal sense, in the general sense? Okay, that is not a mistake, right? Why? Because the value of g is a constant. Okay, everybody is habituated by saying w equals to something, okay, as g is constant. But in the future, if you are going to live on the moon also, then if you wanted to ask the person what is the weight of someone who is living on the moon, he is going to tell a different value. Your mass can be 50 kg and his mass can be 50 kg. Your weight will be 500 Newton, but his weight may be something like 300 Newton. Okay, then it is very much needed to express in terms of newtons. Okay, so this is a perfect example to body forces. Okay, so body forces are nothing but the gravitational forces and electromagnetic force. ఈ ఎలక్ట్రోమాగ్నెటిక్ ఫోర్స్ గురించి మనం ఎక్కువ మాట్లాడాము ఈ స్టేజ్లో, మనకు అవసరం లేదు అది ఇక్కడ. సో వీఆర్ గోయింగ్ టు కాన్సన్ట్రేట్ ఆన్ దిస్ గ్రావిటేషనల్ ఫోర్స్. సో లెట్ మీ రిమైండ్ యూ వన్స్ అగైన్, దిస్ గ్రావిటేషనల్ ఫోర్స్ exerted on a body by the earth is nothing but weight of that body అన్నమాట. ఓకేనండి, మన వెయిట్ని మనం ఇంకో విధంగా ఏమనొచ్చు అంటే, వీ కెన్ కాల్ అవర్ వెయిట్ యాజ్ ఎ సెల్ఫ్ వెయిట్ ఆఫ్ అస్, రైట్? సెల్ఫ్, my weight, right? If I am a tree, okay, the gravitational force acting on me is nothing but weight of me, right? My weight, therefore I call it as self weight. Self. Okay, my weight is not going to change. Of course, if I am not dieting or eating more, my weight will remain constant. Okay, so another name for these gravitational forces or self weight are dead loads. Okay, that is what we are going to see in this next slide. So dead load is nothing but the gravitational force exerted on a body or weight of a body. Remain that, just remember that. Okay, self weight of structure. Of course, ఇక్కడ మనకి స్ట్రక్చర్ అంటే ఏంటంటే ఒక బిల్డింగ్ అయి ఉండొచ్చు, ఒక బ్రిడ్జ్, కెన్ బి ఏ బిగ్ టవర్ ఆర్ సంథింగ్ లైక్, రైట్? సివిల్ ఇంజనీరింగ్ పాయింట్ ఆఫ్ వ్యూ, దిస్ డెడ్ లోడ్ ఈజ్ నథింగ్ బట్ self weight of a structure, self weight of your house, self weight of something, right? So these surface forces are of many types. Okay, these are applied externally, that is what we have seen earlier. So these surface forces are the forces that are exerted on a body by coming into contact, right? So these are called as imposed loads, wind loads, snow loads, earthquake loads. These are the four different kinds of loads. Earthquake loads are the forces or the loads applied on a building or on a structure when there is a seismic activity, if there is an earthquake near that area. Snow loads are exerted on any body when there is a snow. Okay, see here in the figure, there is a house, there is a roof, and on that the snow is accumulated. So this snow load which is being applied on the roof is known as snow load. Okay, so what is the snow load then? What will be the value? The value of the snow load will be equals to the self weight of snow load. Self weight of the snow load. Okay, if I am going to sit at this point, ఓకే, లేకపోతే ఇక్కడ నేను కూర్చుంటే, I will be called as an imposed load or a live load. Okay, I am a surface load. Okay, ఎందుకు? I am exerting myself a force on this floor by coming in contact with this floor. So it is not a gravitational force, I mean it is not a body force, it is a surface force. Okay, I am coming in contact with that. You can apply with your hand force or you can just sit heavily on that floor, right? So whatever it is, you are applying force using your body, right? So if you are sitting on that, the force which you are exerting on the floor will be equals to weight of your body, isn't it? For example, if you took a large size of rice bag of 25 kg and placed it on the roof, then you are applying the force on the roof using a rice bag. Okay, what will be the weight? I mean, what will be the force exerted because of that rice bag? Mass of the rice bag into a gravitational acceleration. So 25 kg into 10, 250 Newton is the load that you are going to apply on that floor using the rice bag అన్నమాట. ఓకే, సో ఇక్కడ రైస్ బ్యాగ్ అంత యాక్చుయేట్ చేస్తుందని నేను ఎలా చెప్పగలుగుతున్నానండి? ఐ క్యాలిక్యులేటెడ్ ది సెల్ఫ్ వెయిట్ ఆఫ్ దట్ బ్యాగ్. ఓకే సార్, ఇందాకలు మరి సెల్ఫ్ వెయిట్ ఆఫ్ ది స్ట్రక్చర్ అంటే డెడ్ లోడ్ అన్నారు, ఇక్కడ మళ్ళీ సర్ఫేస్ లోడ్స్ని కూడా ఈ డెడ్ వెయిట్ ఇది అంటున్నారంటే, సో ఇక్కడ గుర్తుపెట్టుకున్నామా, బాడీ ఫోర్సెస్ని మనం దేన్ని అంటున్నాము? బాడీ ఫోర్సెస్ ఆర్ ది ఫోర్సెస్ దట్ ఆర్ యాక్టింగ్ ఆన్ ఎ బాడీ వితౌట్ coming in direct contact. Dead loads are nothing but an example of such body forces anamata. Okay, next, coming to the next slide, let us go into the nature of these forces. Okay, the three main forces that are going to be studied, okay, are in the nature of the following. The forces can be tensile in nature, compressive in nature, or shear in nature. Okay, and I hope you are familiar with the term shear stress, tensile stress, and compressive stress, or simply stress. What do you mean by stress? Stress is nothing but force by area. Stress is developed because of the forces that you exerted on a given body. If you did not apply any kind of force, there is no stress going to develop in that body. But if you are applying any kind of force, there is going to be a stress being developed in that body. Okay, so it can be a tensile in nature, compressive in nature, and shear. Okay, so let us see what is the difference between these. Okay, so okay, let me go into this. So for example, if you see this body, this rectangular body here, over here, this is the center of gravity of that body. Let us take, this is the axis that is passing through the centroid of the body, and this is going to be called as axis. Okay, So if a force is passing in the direction of axis, then such forces are called as axial forces. See here, the axis is horizontal. The force, tensile force or compressive force, are actually horizontal in nature, right? Same direction, therefore axial loads. These are called as axial loads. A-X-I-A-L, axial loads. Okay, so at the same time there is also a shear force. Shear force. So shear force, when do you call a force as shear force? You call a force F as a shear force when it is acting tangentially to the surface. Tangentially to the surface means ప్యారలల్గా అప్లై చేయడం అంటే తెలుసు కదండి. ప్యారలల్ అంటే ఏంటి? సేమ్ డైరెక్షన్స్. ఏ డైరెక్షన్లో ఇప్పుడు ఏ డైరెక్షన్లో ఇది అప్లై చేస్తున్నట్టు అంటే, సో ఇఫ్ యూ టేక్ దిస్ ఏరియా, this particular area, if you see, this is the plane of the area, right? Horizontal plane, and this force is acting parallel to this surface, right? So here it is different. It is acting perpendicular in compressive and tension, but here it is acting how? Parallel to that surface, tangential to the surface. Therefore this force F is called as a shear force. Remember that shear forces are tangential forces or parallel forces, right? Okay, so but here compressive and tensile, if you see, these act normal to the surface. Normal, see, this is the cross section of that bar, and the angle between these two is 90 degrees, right? So these axial forces always act normal to the surface, normal, perpendicular to the surface. Remember that this term may be a new normal. Okay, normal, NORMAL, normal forces. Okay, so what do you mean by tension and compressional force? Okay, how do you differentiate these two? You differentiated shear force from these two. How? This is tangential and this is perpendicular to the area. But how do you differentiate between these two? Okay, so tensile forces try to elongate the body, stretch the body, increase the dimensions of the body. But compressional forces always try to contract the body, decrease the size of the body. Of course, remember that when tensional force is applied, the body tries to stretch, right? In which direction the length of the body is going to increase? In the direction of force, right? So for example, see here, this is the horizontal length. Let me change the color of the ink so that you can understand. So this is the horizontal direction, horizontal plane. So this is the force in the horizontal direction, right? So this is the axis here. Okay, so now if I am applying tensile force F over here, what is happening is the horizontal dimension is going to increase, right? So what happens to this depth of the member or width of the member? Do you know that? It is going to decrease. Remember that when a tensile force is applied on a body axially, it is going to stretch, but at the same time the other dimension of that bar ఏంటండి, ఒక బార్కి ఏముంటుంది? లెంత్ ఉంటుంది, డయామీటర్ ఉంటుంది. ఒకవేళ ఇది సర్క్యులర్ బార్ అయితే కదా, సర్క్యులర్ రాడ్ అయితే. సో వాట్ హ్యాపెన్స్ ఈస్ ది లెంత్ ఆఫ్ ది బార్ ఇంక్రీజెస్ రాడ్, బట్ వేర్ యాజ్ ది డయామీటర్ ఆఫ్ ది bar decreases anamata. That is what happens when tensile forces are applied. What happens when compressive forces are applied? The horizontal dimension is going to decrease, it is going to contract, but whereas the diameter of this bar is going to increase. Remember that. Okay, but in most of the cases people try to talk about only these two things. Okay, I mean these elongation, contraction only, but there is also a contraction and elongation, increase in dimension and decrease in dimension in the perpendicular direction. అర్థమవుతుందండి ఇక్కడ? This is the perpendicular direction, right? So when a force is applied on these planes, not only this dimension is going to change, increase or decrease, but also the perpendicular dimension is also going to change. Remember that. We are going to see in the next slides about that. Okay. So, and the other thing is, see here in the left side diagram figure here, the direction of the stresses is what is important. The direction of stresses will always be in the direction of force. See here, compare this figure and this figure. Let me clear this for all. Okay, right. See here, what is the direction of tensional force and what is the direction of tensile stress? Same, right? So, and even in the shear, see here, it is parallel to the force is parallel to the surface, and the shear stress is also going to be parallel to the surface in the same direction. Okay, we are going to see how to calculate all these stresses and everything. Very simple equations. Okay, now let me go into this diagram. This diagram is not actually required at this stage for you. Just let me clear a little bit about eccentricity. I hope you heard of this eccentricity. Okay, eccentricity, of course, don't mind my handwriting. Let's just see this figure here. Okay, so if you see here, this body is vertically placed, therefore this is the axis passing through the centroid axis may be somewhere here. Okay, so take this force. So this force is nothing but a compressive force, ante kadandi. This is trying to compress it. So compressive force, some value, don't mind the value, nothing. Okay, just leave that value, whatever it is. So now if you see the point of application of this compressive force, where it is exact point where this axis is actually going through the cross section, isn't it? Right? But here if you see, there is some distance between the point of application of compressive force and also the axis, and the distance between these two things is denoted by small e, which is called as eccentricity. Okay, in this unit it is not much important. We came across these forces, that is why I'm going to tell you this. Okay, you are going to see the effect of eccentricity in your second and third chapter, I think. Okay, and then we are going to discuss a little more there. Now coming to the nature of loading. So we are saying that there are different kinds of loads: wind loads, earthquake loads, and whatnot. Loads because of water, hydrostatic forces, and live loads, wind loads. Okay, so these are the loads. Okay, but the loads can also be classified based on the nature of loading, how they are applied on the body, how the force is applied. Okay, there are three ways in which a force is applied on a body, which you can apply. Okay, right? So first, see the first one, point load or concentrated load. Okay, so when do you call a load acting on a body as a point load? So name itself tells you that a point load acts at a particular point. So if you see here in this diagram, there are three forces or three loads acting on this beam. Just see, this is beam, these are supports. Okay, this is nothing but a beam, wooden beam or something, wood to tayaraina oka beam, and these are the three forces or three loads. So why do we call and how can we call these loads as point loads? ఎలా పిలవగలుగుతున్నాం అసలు అంటే, if you see, this load is actually acting at a particular point. This W2 and W3, all these three forces are acting on the beam at a very particular point or a particular section of that beam, right, at a particular point. Therefore they are called as point loads or concentrated loads. And coming to this second one, this is very interesting because in the design of a column or a beam or a slab and everything, the loads are considered to be uniformly distributed loads. Of course, you are going to see that in your structural analysis subject in your 2-2, right? Okay, so for now, just know the nature of loading. Okay, so it is the same here again. These are the supports, two supports, and this is a beam, and this is nothing but a load. But this load is called as uniformly distributed load, not a point load, isn't it, right? So why do we call this uniformly distributed load? So if you see there, the load is applied on the entire stretch of this beam, right? A load is being applied on the entire stretch of the beam. That means what you did is you distributed a load, isn't it? For example, I have told you this example in previously. Let's take 100 kg of sand. Okay, so place the 10 kg of sand on this beam here. Okay, let us take that the length of this beam is something like 10 meter. So you place this 10 kg of sand over the complete 10 meter length of that beam, right? So if you take a section here and here, two sections, and let there be a distance of 1 meter between each. Okay, so if you take this section of beam, that section of beam, this strip, what is the load acting on the beam between this section and this section? Can you tell me that? This is like this. You bought 10 pens and 10 pens cost 100 rupees. What is the cost of each pen? 100 by 10. Cost of the 10 pens divided by number of pens, right? 100 by 10. 10 rupees each. Here also the same thing. Okay. Complete beam span ఎంత అండి? 10 మీటర్ స్పాన్. దాని మీద ఎంత లోడ్ యాక్ట్ అవుతుంది? 10 kg. సో 100 kg. 100 kg of sand, 100 kg of load is being applied on 10 meter. సో 1 మీటర్ స్ట్రెచ్ మీద ఎంత అవుతుందండి? 100 divided by 10, which is equals to 10 kg. Okay, but you know that we are going to tell in terms of newtons, right? So multiply it with 9.81, roughly 100 newton. ఓకే, ఇక్కడ 1000 kg వెయిట్ అన్నాను. అఫ్కోర్స్ మీ కిందగా చెప్పాను మాస్కి కేజీకి తేడా అంట. యాక్చువల్గా 100 kg అంటే దీని యొక్క వెయిట్ ఎంత అండి? యాక్చువల్గా ఇంత మాస్ ఉన్న శాండ్కి 100 into 9.81, 981 న్యూటన్స్ అనమాట. నవ్ ఇఫ్ యూ సీ దిస్ లోడ్ ఈజ్ యాక్చువల్లీ డిస్ట్రిబ్యూటెడ్ ఈవెన్లీ, సమానంగా ప్రతి మీటర్లో కూడా ఎంత ఉంటుందండి? 10 kg ఆఫ్ శాండే ఉంటుంది ఒక్కొక్క మీటర్కి. ఓకేనండి. సో ఏం చేశారండి? యూనిఫామ్గా డిస్ట్రిబ్యూట్ చేశారు ఈ లోడ్ని. కాబట్టి ఈ లోడ్ని ఏమంటాం? యూనిఫామ్లీ డిస్ట్రిబ్యూటెడ్ లోడ్. నౌ సీ ది థర్డ్ వన్, యూనిఫామ్లీ వేరియింగ్ లోడ్ అంటాం. యూనిఫామ్లీ వేరియింగ్, ది నేమ్ ఇట్ సెల్ఫ్ కంటైన్స్ ది నేమ్ ఆఫ్ ది లోడ్. సో వాట్ ఈస్ వేరింగ్ మీన్స్? వేరింగ్ అంటే మారుతూ ఉండడం అనమాట. సీ దిస్ ఫిగర్ హియర్, ది సేమ్ beam, same supports, but the load which is applied on the complete stretch is not same at each and every section, right? ఇక్కడ చూడండి, ప్రతి సెక్షన్ దగ్గర అంతా ఉంటుంది, ప్రతి స్ట్రిప్లో కూడా. బట్ హియర్ ఇట్ ఈస్ నాట్ ది సేమ్. ఇక్కడ ఏం చేశారు? it is not the same at each and every section, at each and every meter, right? It is actually యూనిఫామ్గా వేరీ అవుతుంది చూడమ్మా, ఎక్కువ తక్కువ అవ్వట్లేదు. ఇట్ ఈస్ నాట్ బికమింగ్ మోర్ అండ్ లెస్, రైట్? It is increasing gradually. It's keep on increasing and reached a maximum value at a particular section. It started with a minimum value, may not be zero all the time, and it reached a maximum value at a section. It increased or varied uniformly anamata. So uniformly distributed low. And if you see this figure, this seems to be like a triangle, right? Triangular. So this load is also called as a triangular load. Triangle, just triangle, triangle, triangular load. Okay, these loads can be of this nature also. So I'm just drawing the figure. This is the support, and this is the case we have seen. And other cases, this is the support, this is the load. Okay, so it started with a minimum value, reached an maximum value at the midsection, and ended with a minimum value here. This is also a uniformly varying load. ఈ వేరియేషన్ అనేది ఎలాగైనా ఉండొచ్చు అమ్మా. దిస్ కెన్ బి ది నేచర్ ఆఫ్ లోడింగ్. అంటే మ్యాక్సిమం దగ్గర స్టార్ట్ అయ్యి జీరోకి రావచ్చు. ఓకే, యాజ్ లాంగ్ యాజ్ ఇట్ ఈస్ వేరింగ్ యూనిఫామ్లీ, దట్ ఈస్ ఎ యూనిఫామ్లీ వేరింగ్ లోడ్. Okay, so I hope you got clarified with this type of loading. Now let us go into the units. Of course, you are very much familiar with all your units you are learning from your school age, right? So let me remind you a few things, very few things. As you know, units are very, very much important. Without units, the dimension has no significance. For example, there is a box. I asked you to find out the width of the box, B, width of the box. You said 100 mm. Okay, but the other person, I told him to find out what is the length of that box, and he said it is 110. Okay, which one is correct? Of course, breadth and length. How should we write actually? So here the dimensions are width and length are nothing but the dimensions, and this mm is nothing but unit. This dimension width has significance only when these units are present besides it anamata. ఈ యూనిట్సే లేకపోతే ఈ డైమెన్షన్కి అసలు అర్థమే లేదు. దేర్ ఇస్ నో మీనింగ్ టు ది డైమెన్షన్ అనమాట. సీ హియర్, ది డైమెన్షన్ లెంత్ ఈజ్ బీయింగ్ ఎక్స్ప్రెస్డ్ as just as a number. There is no unit here. What do you mean by that actually? 110 మీటర్, 110 సెంటీమీటర్, 110 మీటర్, 110 కిలోమీటర్ దాని లెంత్. చూసారా, అర్థం లేదు అక్కడ, జస్ట్ ఒక నెంబర్లో చెప్పడంలో. సో యూనిట్స్ ఆర్ వెరీ, వెరీ మచ్ ఇంపార్టెంట్. సో ఇఫ్ యూ సీ ది యూనిట్స్, length has a unit of meter, area square meter, volume meter cube. Of course, you know you can express all these quantities in mm and centimeter also, right? Mass, kilogram or gram, density kg per meter cube, gram per centimeter cube, అలా కూడా రాయొచ్చు దాన్ని, రైట్? అండ్ ఫోర్స్ ఆర్ లోడ్ హ్యాస్ యూనిట్స్ ఆఫ్ న్యూటన్స్. ఓకే, అండ్ మూమెంట్ అంటే మీకు ఆల్రెడీ తెలుసా? What do you mean by movement? Movement is defined as force into perpendicular distance, right? So force Newton into perpendicular distance. Distance can units of meter. Therefore, the units of movement is nothing but Newton meter. And at the same time, what are the units of stress? Stress is the most repeatedly heard word in this subject. And ఎన్నిసార్లు వింటారంటే అన్నిసార్లు వింటారు ఈ సబ్జెక్ట్లో స్ట్రెస్ అనే వర్డ్కి. సో యూ మస్ట్ బీ వెరీ మచ్ అవేర్ ఆఫ్ దీస్ యూనిట్స్. సో స్ట్రెస్ కెన్ బీ ఎక్స్ప్రెస్డ్ యాజ్ న్యూటన్స్ పర్ స్క్వేర్ మీటర్. ఓకే, ఫోర్స్ పర్ యూనిట్ ఏరియా కాబట్టి యూ కెన్ రైట్ దిస్ యాజ్ న్యూటన్ పర్ సెంటీమీటర్ స్క్వేర్, న్యూటన్ పర్ mm square. But our habit of writing stress in the units is Newton per meter square or Newton per mm square. We rarely write stress in terms of centimeter, Newton per centimeter square, very rarely. Okay, and nobody prefers to write in that. Okay, now we also express these terms in terms of pascals also. Pascal is nothing but an other unit of stress. What is pascal? Pascal, 1 pascal is equals to 1 newton per meter square. Of course sir, already there is a unit here. Why do we give another unit like pascal? Actually Pascal is a scientist, you must be aware of him. Okay, so in the honor of that person, we have named this Newton per meter square as Pascal. So 1 Newton per meter square is nothing but Pascal. So stress has units of Pascal also. So Pascal, kilopascal, megapascal, gigapascal. Kilopascal and 10 to the power of 3, 10 to the power of 6 ante mega, 10 to the power of 9 ante gigapascal. అంటే ఇక్కడ చూడమ్మా, 10 to the power of 9 పాస్కల్ అంటే ఎంత, 1 జిగా పాస్కల్. ఇంకో విధంగా ఎలా చెప్పొచ్చు అంటే 10 to the power of 9 పాస్కల్ అంటే 10 to the power of 9 న్యూటన్ పర్ మీటర్ స్క్వేర్. 10 to the power of 6 పాస్కల్ అంటే 10 to the power of 6 న్యూటన్ పర్ మీటర్ స్క్వేర్. సో రిమెంబర్ దీస్ డెఫినేషన్స్. ఓకే, సో టెంపరేచర్, degree centigrade. This is how you express the temperature. So let me go into this free body diagram. So this is very important when we are going to deal with forces and all, reactions and everything. Okay, so what is an equilibrium body? Equilibrium lo oka body undi ante enti? What do you mean by an equilibrium body or a body is at equilibrium? What do you mean by that actually? ఏంటి అసలు అర్థం ఏంటి ఈక్విలిబ్రియంలో ఒక బాడీ ఉందంటే? సో వెన్ ది నెట్ ఫోర్స్ యాక్టింగ్ ఆన్ ఏ బాడీ ఈజ్ జీరో, నెట్ ఫోర్స్ యాక్టింగ్ ఆన్ ఏ బాడీ ఈజ్ జీరో, then such body is known as a body which is under equilibrium. The perfect example is like this. There is a box here. Some person is pulling from this side, some person is pulling from this side. Take this as F1, take this as F2. If F1 is equals to F2, what happens is the net force acting on this body is 0. Sorry. So how it is 0? It is 0 because the force F2 and F1 are same in magnitude but opposite in direction. Therefore the net force will be equals to 0. What happens if the direction of this F2 is actually this direction? Then the net force will be F1 plus F2. Okay, so what I mean to tell you is actually if the net force is 0, this body is not going to move anyway. So if this is different or F1 is actually greater than F2, what is happening there? Since F1 is greater than F2, the net force is not going to be 0, right? So ఏమవుతుందండి, F1 is greater, right? Therefore this body tends to move in this direction. మీకు ఈ తాళ్ళతో ఆడేది గుర్తుంది కదండి, గేమ్ జనరల్గా ఆడతారు పండగ కదా. దెర్ ఈజ్ ఎ టీమ్ ఆన్ బోత్ సైడ్స్, దెర్ ఈజ్ ఎ లార్జ్ రోప్ on both sides. These people are going to hold that rope and going to pull. Who is going to pull stronger is going to win, right? So the same game is happening here. If both the people are playing same kind of force, same amount of force, they are just going to remain there itself, right? It's a funny thing. Okay, so when we are studying such equilibrium bodies, it is very much important for us to draw the free body diagram. Note this point, right? Okay, whenever you are studying such equilibrium bodies, it is very much important to to draw these figures, free body diagram. Okay, let me show you in a very simple example. So there is a box here, and you are the person. You are trying to pull this box in this side. Okay, so what do you do? Yeah, you hold that box with your hands. So this is your hand. Okay, and you are pulling in this direction. You are applying force at that point, isn't it? Let me give you a color picture. Okay, so this is the point where you are applying force. So this is the picture that is visible to anyone, right? మీ ముందర నేను సీట్లో కూర్చొని ఉంటే ఒక రైల్వే స్టేషన్లో కానీ ఎక్కడైనా, దిస్ ఈజ్ వాట్ ఐ సీ. దెర్ ఈస్ అ బాక్స్ అండ్ యూ ఆర్ ట్రైన్ టు పుల్ ఇట్. సో దట్ ఈస్ ది సీనరీ, right? But in order to analyze you and that body and the forces exerted on it, I am going to draw a simple picture for myself, the body. But instead of drawing your face and your body, I am just trying to represent this force F like this. This F is nothing but the force which you have applied on the body with your hands, pulling it in this direction. So what I did is, ఏదైతే ఫోర్స్ అప్లై చేస్తుందో మీ హ్యాండ్ అని నేను తీసేసి దాన్ని దేంతో రిప్లేస్ చేశానండి? ది ఫోర్స్ దట్ యువర్ హ్యాండ్ ఈజ్ అప్లయింగ్. ఓకే, ఐ రిప్లేస్డ్ యువర్ హ్యాండ్ విత్ ది ఫోర్స్ బీయింగ్ ఎగ్జర్టెడ్ బై యువర్ హ్యాండ్ అట్ దట్ పర్టికులర్ పాయింట్, రైట్? అంటే ఇక్కడ ఆ ఫోర్స్కి కారణమైన ఆబ్జెక్ట్ని నేను పక్క తీసి ఆ ఫోర్స్ని మాత్రమే నేను చూపిస్తున్నాను అక్కడ. ఓకేనండి. సో దిస్ diagram is called as a free body diagram. Okay, so see the below figure once, just a second. So what did you understand? Let me show you here. This is the beam, this is the column B, column A, and this is load. What is this load? Uniformly distributed load. Okay, so this load is being applied. For example, consider it as W per meter. Okay, this is 10 meter distance. So remember that UDL is always applied, represented as W per meter. ఒక మీటర్కి ఎంత లోడ్ ఉందో అదే రాస్తాం అన్నమాట యూడిఎల్ఏ. ఇందాక మనం అనుకున్నట్టుగా 100 kg ఆఫ్ శాండ్ పెట్టారు 10 మీటర్ బీ మీద, ఒక్కొక్క మీటర్ మీద ఎంత యాక్ట్ అవుతుందండి? 10 kg. సో అక్కడ ఏం రాయాలి? యూనిట్స్ ఎలా రాస్తాం? లోడ్ని రిప్రజెంటేషన్ చేస్తాము అంటే 10 kg per మీటర్ అని రాయాలన్నమాట. సో ఇక్కడ కూడా అంతే అనమాట. సో మీకు టోటల్ యూడిఎల్ లోడ్ ఎంత అనేది కావాలంటే ఏం చేయాలి? డబ్ల్యూ దట్ ఈస్ యాక్టింగ్ పర్ మీటర్ ఇంటూ లెంత్ ఆఫ్ దట్ బీమ్ ఎంత అండి? 10. అంటే ఎంత? 10 డబ్ల్యూ అనేది టోటల్ లోడ్ అనమాట. బట్ మనం అలా రాయం, వి రిప్రజెంట్ పర్ మీటర్ అన్నమాట. అది గుర్తుపెట్టుకోండి ఒకసారి. సో ఇఫ్ దిస్ 10 డబ్ల్యూ ఈజ్ ది టోటల్ లోడ్, ఈ కాలం ఎంత తీసుకుంటుందండి? 10 డబ్ల్యూ బై 2. ఇది 10 డబ్ల్యూ బై 2 అనే లోడ్ తీసుకుంటుంది అనమాట. ఈ కాలం ఈ లోడ్ తీసుకుంటూనే, వెన్ ది కాలం ఈజ్ యాక్చువల్లీ టేకింగ్ దట్ లోడ్, దిస్ కాలం ఈజ్ ఆల్సో గోయింగ్ టు ఎగ్జర్ట్ ఏ రెసిస్టింగ్ ఫోర్స్ అండి. గుర్తుపెట్టుకోవాలి ఈ టర్మ్ని మీరు. మనం ఏదైనా ఒక బాడీ మీద వెన్ యూ ఆర్ అప్లయింగ్ ఏ ఫోర్స్ ఆన్ ఏ బాడీ, దట్ బాడీ ఈజ్ ఆల్సో గోయింగ్ టు అప్లై సేమ్ అమౌంట్ ఆఫ్ ఫోర్స్ బ్యాక్ ఆన్ టు యూ. ఓకేనండి. అందుకే మీరు కోపంలో వచ్చి ఏదైనా ఒక గోడని గట్టిగా గుద్దారనుకోండి, ఇఫ్ యూ హిట్ యువర్ వాల్ విత్ యువర్ హ్యాండ్, వాట్ హ్యాపన్స్ ఈజ్ యూ ఆర్ గోయింగ్ టు గెట్ పెయిన్ యాక్చువల్లీ, రైట్? గోడకు కాదు వచ్చేది. ఎందుకు? బికాస్ దట్ వాల్ ఈజ్ ఆల్సో గోయింగ్ టు అప్లై సమ్ ఫోర్స్ ఆన్ యువర్ హ్యాండ్ అనమాట, ఎక్కడైతే డైరెక్ట్ కాంటాక్ట్లోకి వచ్చారో. ఓకే, సో రిమెంబర్ దాట్. సో ఇప్పుడు రియాక్షన్ ఎంత ఉంటుందని, ఏదైతే ఈ కాలం తీసుకుంటుందో, వాట్ ఈస్ ది లోడ్ బీయింగ్ టేకెన్ బై దిస్ కాలం 10W/2, and this column is going to apply same amount of reaction. So if you see the left right hand diagram, the reaction, this RA is nothing but reaction anamata. Reaction is represented with R. So this reaction RA is the reaction applied by column A on this beam at this particular end, and B here. Okay, so what is the value of RA? 10W/2. Okay, you will understand further slides and classes, so don't worry, okay, about simple things. Okay, this is nothing but a free body diagram. Therefore, we are removing the columns here, actually, which are responsible for the reaction RA and RB. Okay, we are replacing those columns with the reactions offered by those reactions offered by those columns anamata. Remember that. Okay, so let me go into the next slide. Okay, so if you see here, we are going to discuss about stress. So stress is the most important parameter, or the term that you are going to hear repeatedly, as I said earlier. So what is stress and how do you define stress? Okay, so as I said earlier, when you are applying some force on a body, that body is also going to apply equal and opposite force onto your body. Okay, if you hit a wall with 10 kilonewton, that wall is also going to apply 10 kilonewton of reaction onto your hand. Okay, so reaction is represented by R, force is applied by represented by capital F. So what do you mean by this stress? Stress is nothing but the resisting force. If you see this slide, resisting force per unit area. Okay, resisting force divided by area is nothing but stress. But I said earlier to you, the resisting force is actually equal to the force actually you applied, kada? So therefore you can define this stress as the force applied divided by area. So force applied divided by area is equals to resisting force developed in the body divided by its area. So what area? Okay, so the area on which this force is acting either tangentially or perpendicularly, that area is to be taken here. See the figure here. We have a figure here. So this is the force F and this is the force F. Remember, these are the axial forces and compressive in nature, tensile in nature, because it's trying to stretch the body. And this is the cross section force, cross section of that bar. Cross section of the bar ఎలా act అవుతుందంటే perpendicular. As I said earlier, this compressive and tensile forces act always perpendicular to the cross sectional area. సో క్రాస్ సెక్షనల్ ఏరియాకి యాక్ట్ అవుతున్నాయి. సో ఇప్పుడు ఏరియా అంటే ఏమైనా స్ట్రెస్ అంటే దిస్ ఫోర్స్ ఎఫ్ డివైడెడ్ బై ఏరియా, క్రాస్ సెక్షనల్ ఏరియా. Okay, or you can write R by A also, nothing wrong. So what will be the direction of R here in the diagram? So let me show you. This is R. Of course you can represent it anywhere. Okay, some people do it at exact at the midsection. Okay, no problem with that. So this is the final equation for stress. Okay, so as a note, once again, force applied externally is equals to resistance developed or offered by material itself. So coming to the types of stresses, stresses are actually classified into three ways: direct or simple stress, indirect stress, combined stress. Okay, so the direct stress or simple stress is the matter of importance in this unit. Okay, that is what we are going to study further in this part of unit. And direct stresses and combined stresses are studied in the further units, unit 3 and 4, I believe. So these direct stresses are classified into two types: shear, normal. And these indirect stresses are classified into torsional stress and bending stress. Okay, so ఈ రెండింటిని ఎలా క్లాసిఫై చేసామంటే we classified this normal, direct stress into shear and normal stress based on the manner of acting. And we have said earlier, if this is a box, this is the shear force, and this shear force will give rise to shear stress. Tau is used to represent the shear stress. So shear stress is acting parallel, therefore it is a kind of a stress. And normal stress అంటే ఏంటంటే, if this is the surface, this is the center, they act perpendicular if it is a tension or compression. If it is a compression, it acts this way, and if it is a tension, it acts upwards. That's it, right? But whatever it is, they always act perpendicular. Perpendicular is can be also called as normal, NOR-MAL. Therefore the perpendicular stresses are nothing but normal stresses. See. Okay, so this is what I have said earlier. So generally stress అంటే ఎలా డిఫైన్ చేస్తున్నామండి? Force by area, right? So now shear stress is nothing but shear force by area. That's it, that's simple. Okay, shear force by area. See, tangential force is nothing but shear force, and the area, surface area on which it is acting tangentially. And this is another example. These are two plates, this is a bolt, and this is the section on which this force is being applied. Actually ఇక్కడ చెప్పాలంటే చూడండి, even though the force P is applied on these two plates, actually because of this rivet, it gets here. The force P is acting actually here, and the force P is acting actually here. Sorry, this is not the direction, this is the direction, right? So P, so the here and this. So the rivet, if you see the rivet, half of the rivet is being pulled in this direction and the other half is being pulled in this direction. So the direction of this P is actually in the direction of this cross section, right? క్రాస్ సెక్షన్కి టాంజెన్షియల్గానే కదా ఉంది, క్రాస్ సెక్షన్కి ప్యారలల్గానే కదా ఉంది ఫోర్స్ అనేది P. దేర్ ఫోర్ దిస్ ఈస్ కాల్డ్ as a shear force, and because of this shear force in this cross section a shear stress tau is going to develop. So it is going to shear, fail. Okay, let's go into the next. So normal stresses, as I said to you earlier, these are the perpendicular forces acting on an area. Okay, these are tensile in nature, compressive. If you see this figure, this is the tensile force acting perpendicular to the cross sectional area. So this is nothing but a normal force F, which is tensile in nature. But as it is acting normal to the surface, the stress because of this force is nothing but a normal stress. So here if you see this F, this is compressive in nature, but it is acting perpendicular to the surface, therefore it is called as a normal stress. ఓకేనండి, ఎఫ్ అనేది ఫోర్స్, కంప్రెసివ్ ఫోర్స్. ఈ కంప్రెసివ్ ఫోర్స్ వల్ల కంప్రెసివ్ స్ట్రెస్ వస్తుంది. ఆ కంప్రెసివ్ స్ట్రెస్ ఎలా ఉంటుందని క్రాస్ సెక్షన్కి పర్పెండిక్యులర్ డైరెక్షన్లో వెళ్తుంది, కాబట్టి ఆ కంప్రెసివ్ స్ట్రెస్ని నార్మల్ స్ట్రెస్ అంటాం. రిమెంబర్ దాట్ ది నార్మల్ స్ట్రెసెస్ ఆర్ రిప్రజెంటెడ్ విత్ సిగ్మా, అండ్ వేరస్ shear stresses are represented with tau. Okay, so we have seen this earlier. Let me just remind you in a second, right? Okay, so stress is equals to force by area. So units are force kilonewton, area meter square. Kilonewton per meter square, this is nothing but kilo pascal, since Newton per meter square is equals to 1 Pascal. This is nothing but mega Pascal. This is nothing but gigapascal. Okay, you must remember these units. So 1 Newton per meter square is 1 Pascal. We have also another system of units, MKs. We are not using that system nowadays. Okay, it is an outdated, but just try to know that, because sometimes you may be given problems in terms of these units అన్నమాట. సో రిమెంబర్ దాట్. సో ఫోర్స్ స్ట్రెస్కి ఏంటండి, ఫోర్స్ బై ఏరియా. వి డినోట్ విత్ కేజీ ఫోర్స్, కేజీఎఫ్ అని రాస్తాం ఫోర్స్ని. కింద ఏరియా యాజ్ యూజువల్గా సెంటీమీటర్ స్క్వేర్, మీటర్ స్క్వేర్, ఎంఎం స్క్వేర్, ఎనీథింగ్ కెన్ బి రిటన్. సో దిస్ ఈజ్ ది రిలేషన్ between Newton per mm square and 1 kg per centimeter square. So just verify this equation. That is your homework that I have given you earlier. So try to prove this. Is this actually correct or wrong? Okay, it can be a correct but wrong. Okay, I'm just giving you a homework. Okay, prepare that. Let me conclude this with this slide, today's class. Okay, so these compressive stresses, tensile stresses and shear stresses are going to actually lead to the failure of the member, failure of the body. How the body is going to fail? See here, if you see the tensile stresses here, these tensile stresses are actually trying to split the body. So the body gets splitted into two halves, and that is how it fails. But if you see the compressive stresses here, because of these compressive stresses, this body is going to be get crushed అండి. చూడండి, ఎప్పుడైనా సుత్తతో కొట్టి ఏదైనా పగలగొట్టాలంటే ఏం చేస్తుందండి, వీ క్రష్ ఇట్. లేకపోతే చాక్ పీస్ నేల మీద వేసి దాని మీద అడుగేస్తే ఏమవుతుందండి, ఇఫ్ యూ స్టెప్ ఆన్ ద చాక్ పీస్, ఎస్, ఇట్ గెట్స్ క్రష్డ్, రైట్? So that is how a member or a body fails, because of compressional stress. And this splitting of this body in this manner is actually known as shearing అన్నమాట. shear of అంటాం, లేదు అంటే shearing. Okay, so this is how these shear stresses fail a body. So in today's class we have seen about the basic definitions and fundamental units and the types of stress and how this stress is causing a member or a body to fail. So in the next class we are going to see about strain. Okay, so with this I am going to conclude today's class. Okay, so thank you everyone once again.